Okay, so this talk's going to be slightly different because I wouldn't by any means claim to be a mathematician. So I want to set you a problem and get you to tell me how to solve it. So the problem's there in orange. What I want to do is use imaging to be able to identify a person 10 kilometers away. And that's a challenge. It's not going to be easy for you to solve this. The picture on the right is just, it's a chain home radar tower that's on our site. And it's, yes, yeah. So it essentially, I think that's the only one that still survives, and it's just to show we've got a long heritage in sensing. So as an overview, I'm going to talk a bit about the challenges that you're going to have in solving this problem. Not least is customer requirements. I mean, we're engineers, and we actually have to service a customer, and they have some quite challenging requirements. The physics, well, you can't overcome physics, so you've got to have some way to come around the problems that gives you. The environment, what happens when it's foggy. And then finally, I've added some on system. And the main reason for that is a lot of the techniques that are used are being developed in isolation. And I'd like you to tell me how they're best combined together, what the best way to use them is. I'll talk a little bit about the tools that are available, image quality improvement. Now, I apologise up front. I'm sure there are people that know far more about these algorithms and so on than I do, so any mistakes are wholly mine rather than BA systems. And also, just to raise the possibility that it might not be all about raising the image quality. There may be other techniques you can use with poor image quality. Coming back to the system considerations, a few quick conclusions, and then trying to capture the questions that are particularly important to me for you guys to tell me how to solve. So specific challenges, customer requirement. It's always going to be cost, but cost doesn't necessarily mean cheap. It means value for money. So for example, if you're trying to protect this thing, you can probably afford to spend a lot more on your sensors than if you're trying to protect this thing. Size, weight and power. Well, I'd feel really sorry for this guy up here if he had to lug that 10 kilometers. Real-time operation. What I mean by that is I want the information quickly enough to do something useful with it. If I can detect there's someone 10 kilometers away, but it takes me a day to detect it, well, he'll have disappeared. Ease of use. Well, again, lugging that 10 kilometers is particularly easy, but I'm also thinking here that you don't want too many knobs and things to have to twiddle and to understand how to twiddle them. And that comes on also to training required. I don't want to have to use PhD qualified people to do this because that adds a whole load of expense, and also you've only got a few of them. What happens when they go off sick and so on. Day-night. Do you want to be able to do this at night? Oops, sorry. If so, that image, I would argue, which is a thermal image, which is in the sort of longer wavelength region, it'd be a lot harder to identify him than it would him. And platform, again, the sort of frequency of vibration and therefore the frequency of the blur is going to be different for something like that and something like that. But there are other things such as, it's probably quite relatively easy to fit something that size on this, probably less easy on that. The physics, I'm going to come on to why we're going to, or you're potentially going to need the big lenses like this here. But part of that is, if you're making a big lens, you've got to make it accurately, and if you don't make it accurately, you get aberrations, and that changes the point spread function and blurs the image. Diffraction and lens diameter, I'm going to talk about in a bit of detail. Optical signal to noise power. If it's dark, you're not getting a lot of photons in. There's noise in the detector, and you've got to actually be able to detect the signal above the noise sufficiently to give you the contrast to recognize someone. And again, pointing stability and accuracy. He doesn't only have to be a PhD, this guy, but he's got to be quite strong to lug it, and then he's got to point it to a great accuracy if he's trying to recognize someone at 10 kilometers, and I think, I wouldn't fancy holding that. And environment, illumination, well, that comes down to things like day-night, but, are there enough photons coming in for you to be able to get enough contrast? Weather, there's a picture here of haze. I think that might be Hong Kong, I'm not entirely certain. But, if you're imaging 10 kilometers away, how much light is going to get through that? Obscurance, if there's smoke drifting across or something like that, how are you going to see through those? Turbulence, I'm going to talk about in some detail. And finally, motion. Again, the sort of blur characteristics of this are going to be quite different to the blur characteristics of that. So those need to be dealt with. System considerations, and I'm probably going to repeat this a few times, but There are lots of mitigation strategies. We'll talk about a few of them later on in the talk. Each has strengths and weaknesses. But I believe I'm right in saying they've all been developed in isolation. For all these problems, you're not going to be able to use a single approach to encompass the whole set of problems. But together they could provide a toolbox. So the problems here is, how do you use them together? Can they be used separately? Do they commute? Do you have to use them in a certain order? How to combine them? And also, how do you know when you've done it good enough? Because you can optimize all these things, but it's going to take time. You've got a lot of processing to be done. So you need some measure of saying, some measure that the system can understand, of saying, yeah, that's good enough. I don't have to spend a lot more time optimizing this before I start on the next situation. I talked about not needing PhDs. You know, you don't want someone having to operate a control rack like this. So you actually want the system, ideally, to be intelligent and adapt itself. And also, there's a thing called vigilance decrement. If you're looking at a surveillance system, your attention span fails and you start missing things after about 20 minutes. So ideally, you want the human looking at the system, looking at things of interest, but you want the machine to be able to detect those things of interest so that then he can apply the cognitive, he or she, sorry, can apply the cognitive power in order to actually get the best value out of the system. But then the automated system might need different parameters in terms of the image quality to the human. So how does that affect it? You're going to tell me in a bit, I think. So I'm a physicist at heart, so one of the first problems is diffraction. If you've got a point on the target, diffraction through the lens means that it actually gets blurred by the time it gets to the image plane. That blurring depends on the aperture. The bigger the aperture is, the smaller the blurring, and you can actually, if you've got a nice big aperture, you can separate these two spots. If the aperture gets smaller, you can just about identify there's two spots there, but if it's too small, the two coalesce together and you can't see it. What this is related to is the wavelength. So the longer the wavelength is, the bigger the diameter has to be to get the same point spread. So that means I have to increase the diameter to get the resolution, but if I use a longer wavelength, which I might want to use for one or two reasons, I have to increase it even more. So to put some numbers on this, you can argue about what the resolution needed is to recognize people, but if I want to recognize if I want to detect features on a building, those might be about the size of a meter. So that 1 kilometre, you can do that with a mobile phone. That's not too difficult. But if I want to identify a stranger, then the resolution on the subject has to be about 1 millimetre. What that means is, just using this basic formula, the lens diameter is getting on for 8 metres. Well, that's big. You've got all the problems with lens aberrations and things, but also it's heavy. I mean, this is just an assumption. Say, on average, it's about 5 centimetres thick, but that's about the weight of about 6 Ford Fiestas. So again, you know, you're not going to fit that on a small land vehicle. Turbulence is the other physical effect I'm going to talk about a bit. As air either heats up or passes obstacles, so the wind goes past obstacles, you get eddies created. Those eddies start out reasonably large, but then they gradually give energy into smaller eddies and smaller energies, and then eventually, when they get small enough, they dissipate as heat. The eddies will have varying refractive indices. And what that means is that the path of light going through this path is going to see a slightly different refractive index to the path of light going through this path, and you get a distortion on the wavefront hitting the lens. You're probably familiar with it if you look at stars as twinkling. And again, it's a weak dependence, but it does improve with wavelength. So again, the wavelength choice, assuming everything, you've got a free choice, which you won't have, but assuming you've got a free choice, turbulence improves with longer wavelength. However, the diffraction problem gets worse with longer wavelengths, so they're in opposition there. There's a few pictures here showing sort of from a paper showing the effect of increasing turbulence. And you can see sort of in the first one, there's some features there. If you're lucky, if it was slightly higher resolution, you'd probably be able to read the name. You wouldn't stand a chance down here. The effect of turbulence is it's to do with the correlation distance on the objective lens. If the wavefront correlates, then effectively you can see through that. If the wavefront doesn't correlate, you get a distortion. And what that means is the effective diameter of the lens that you are imaging is according to that correlation length, which typically is about 2 to 5 centimeters, unless you do something about it. And the other thing is it's a dynamic effect, so it varies on the scale of sort of tens to hundreds of hertz. So you do have to have a fairly fast loop if you're going to control it directly. So this is an approach that's used to improve the diffraction problem. What happens here is you have to shine a coherent light source, in other words, a laser at the target, and then you can move your objective lens, and provided the different images get more than 65% overlap, you end up with a result that's the equivalent to having an objective lens that's the sort of outer edges of where that objective lens is. So you've got to have overlap, you've got to move it, so it's going to take some time. But you get a result here that the left-hand red image, or the one that's bordered in red, is using a cheap camera. The right-hand one is using an expensive camera, $150K, and you've got an improvement. You've changed the diameter of the lens from 75 millimeters to 215 millimeters. So your resolution should have improved by about a factor of 3. But the one in the middle uses a cheap camera, but it's using this technique where they've captured 81 images moving the camera around. I think this is all simulated, actually, to be fair. And that is the best quality image of the lot. And if you look at the detail of the eye on the right-hand side, you can start to see sort of where the pupil is and so on. You can certainly see sort of the edge of the eye and things far more clearly. So we might have a technique that helps with diffraction. We're going to talk about 3 types of turbulence mitigation. Pre-detector processing, what that is related to is actually in correcting the wavefront due to the turbulence before it goes through the objective lens. So the image here is a BAE Systems Labs deformable mirror. I think this one's particularly a zonal mirror, so it's got as you deform it, gives a sort of profile like this, but you can get ones that are sort of higher order profiles and more complex shapes. So I'm going to talk a little bit about what's called adaptive optics, which is what this is in wavefront sensing. Computational imaging, well, in this one you change the hardware and you do some processing after you've captured the image, because you don't capture a standard image to recover the image. I'm going to talk about planoptic imaging a little bit there. And then post-detector processing is just purely in the software. You've captured the image using a conventional camera, and then you use some software to try and recover the image or at least improve it. And I'm going to talk about deconvolution in there. So pre-compensation, I'm trying to, remember that distorted wavefront earlier on, I'm trying to correct that. So what I need to know is what that distortion is in the wavefront. Now, in astronomy, you typically use a point source, guide star or something that's close to the thing you're trying to look at. And that point source is imaged through a series of small lenses which sample the wavefront at different points across it. And depending on where that then focuses onto, tells you about which way that wavefront is pointing. So by calculating that, you can then get the signal to put back into that deformable mirror. Unfortunately, we haven't got nice convenient things to try and image like stars, but there is a similar technique which can be used, which is shown in the bottom here, where you take the scene and you image it through a whole series of small lenses. You get all these tiny images, which you then correlate to one another, or convolve with one another rather, to find out what the displacement, the relative displacement is, and that tells you about the wavefront. Similar technique is planoptic sensing. Now this was a camera technique developed so that you could take one image and actually change where the focus is in it. what happens is, on the top right here, you can see the point in the object plane is imaged to a set of small lenses, so similar to before. But now, behind that set, and offset from it a bit, you've got your focal plane array. So depending on which pixels are illuminated there, you know which direction in the objective lens the light is coming from. And what that means then is those pixels give you some information because of, again, of the movement of those sort of minor images as to what shape that wavefront is. As I say, it's conventionally used for computational refocus, but recent papers have sort of started to look at this to allow turbulence to be corrected. And in this case, you don't need the mirror. Because you've got all the information there, you do some quite complex processing to recover the image and also to compensate for the wavefront distortion. But it does depend. What you're doing at the right-hand side is you're separating the light that would normally be focused onto 1 or 2 pixels onto many pixels, and the noise stays the same in the receiver. So it does need high signal to noise, or otherwise it won't work, because you'll just lose the signal in the noise on the receiver. And there's some examples here. I think they're simulated again. You've got the original image, they've simulated a blur, they've taken a planoptic image, and they've restored it. Now, the one on the right is just simply because the restoration they used circular lenses, and the impact of that was there were bits that were blind, but there are ways to overcome that, you know, through using more rectangular lenses. Post-compensation, I've picked multi-frame blind deconvolution. As I say, the people that will understand this far more than me, but the essence is you take a blurred image and somehow you come up with an estimation of what the blur is and then use a deconvolution to restore the image. I believe what you do is you use a sort of weighted function of the error and try and optimize that, but again, I'm not too clear on the details of that. But there are other techniques as well, depending on what details you know about the image. So for example, if you know what the frequency characteristics are of the image and the additive noise, you use a Wiener filter, which is effectively a spatial filter or a spatial gain technique, which is shaped so that you don't amplify the noise where there's not much signal. Similarly, if you know the additive noise, you use a regularized filter. And Lucy Richardson is if you know, for example, if you've got a badly designed camera, but you can quantify what the point spread function is, that one can be used to recover the image. So all I've been talking about so far is about trying to de-blur images and actually make the image as sharp as possible. But are there ways to retain a blurred image but have enough information there to still be able to recognize someone? So there are some reports that gait is quite personal. It's a sort of fingerprint. So if you've got a blurred image but you can apply a skeletal model to it, have you got enough information then to actually be able to recognize someone, albeit you'd need to know what their gait was like in advance. And then there's things like hyperspectral cameras, which have very fine spectral, they take spectral images, so you get a whole set of images with very fine filters on there, albeit you need enough signal to noise. But can that tell you something about someone? I don't know, but it's possible. And can you use a third dimension? So this is effectively a laser flash photo, but you can time when your shutter is open to get the light coming back. So I would argue that that image there, I can just about see what it is because I know what I'm looking for, but it's quite indistinct. But if you time that gate at different depths, you actually start to see it's a cottage with the roof missing. Now there are ways to make it far more resolved in that and not having to take multiple pictures. But if you can get 3D definition, do you still need the same resolution in the XY plane if you've got some information in the Z plane as well? So that open question may have some benefit, may not. System architectures, I think I've sort of touched on this, but the different techniques have strengths and weaknesses. My belief is that whatever solution is going to need a tailored blend of them according to the existing conditions, in particular the environment. Question for the audience is, what's the best architecture? Is it parallel? If so, how do you fuse the results? If it's serial, does it have to be in a particular order? And a key thing is how do you make it fast, because you've just introduced a whole extra amount of processing. And then also, you know, the environment's changing. You know, if the sun goes behind a cloud, all the turbulence characteristics change abruptly. And how can we tune the individual techniques to give? And I started putting the best, and I purposely crossed it out, because we don't need to give the best result. We need to give a good enough result as quickly as we can. But how do you do that autonomously and so on? Because you don't want the PhD doing it. So the conclusions is I don't think there's a solution for this without computational imaging, and probably the majority of the solution is computational imaging. There are physical limitations, particularly the aperture, but you know, if you've got strong turbulence and you don't mitigate it, you can put as big a lens on there as you like, but it's not actually going to help. There are emerging techniques coming out, which, as I say, range from things that involve hardware to purely software. But the solutions have to be compatible with end-user requirement. I think in particular, the speed is going to be quite important here. And also address end-users' problems. I think inherently they do because of the way I set the challenge, but you don't want to be solving something that doesn't do something useful. I'm an engineer, so I would think that way, I suppose. And a systems approach is needed to make sure that you get the maximum possible from the system, that you're not just looking at one technique in isolation. So some questions. I think I've been scattering these as I've gone through, but what is success? I think we need a measure of success to be able to, a sort of quantifiable measure of success, not just that Fred recognised rows. And what does that mean for the system requirements? How do we use the tools best together? If they're non-linear, we need to understand that. So, for example, I'd argue if you did a lot of the image reconstruction and then took the signal from that as the input into an adaptive optic, you're probably not going to be using it in the best way because you'll have taken some of the information out. We need to satisfy the end user's needs. How do we do that? I don't want expert operators, as I've explained. Can I get it self-tune? How do I do it fast enough? And also, you know, how do we maximize the range of operating conditions? I want to use this for as many different situations as I can, not just on a sunny day under ideal conditions. And really, you know, the end user, we'd like to really, really please him. So if we can make the recognition autonomous, that'd be great. But then does that change the requirements on the system? Are we trying to optimize for different parameters than we would be otherwise? I've got to thank Lionel Kent because I've shamelessly pinched some of the content from one of his slide packs, who's one of my colleagues at BA Systems. And any questions? Thank you, by the way.
Question, but I can't recognize it too far.
So your problem is very similar to what people use in microscopy, in, for example, cell microscopy or fluorescence microscopy, where optical challenges are very similar, blindly blurring and so on. There, I think one key is that you really have calibration that you can apply and that you have validation of your data with good ground truth situations. How challenging is it in your case to create ground truth data? And yeah, because due to the long range and due to the outside that you have to create your experiments.
I think it's going to depend on the specific situation. So, for example, if you're trying to protect, I don't know, Westminster Palace, and the camera's always pointed in the same direction, then at least you can, over time, pick up a very good image of the sort of the background, if you like. In which case, that's the calibration. But if it's something that's mobile, you maybe set it up for an hour, I'd imagine it'd be a very, very difficult problem to calibrate it. Whether you can do any sort of computerized models, for example, of the buildings in the area and things, and feed that into it, that may be possible, but that requires quite a lot of information up front. You know, and you may not have time to prepare that. Okay, thank you.